Okie dokie. Ooh. So, today we're pretty much going to finish up our little adventure into limits. All right. Tomorrow after the quiz, I'm going to show you like one more thing called the derivative, which is like essentially teaching you some calculus tomorrow, but just an easy little bit, putting together some things we've seen in the past. So anyway, today we're going to evaluate some one-sided limits. Okay? We've already kind of looked at the idea of evaluating one-sided limits. We talked about evaluating from the left-hand side, from the right-hand side, right? We've seen situations where the left-hand side and the right-hand side disagreed, right? When we talked about those absolute values, right? And so since they disagreed, we said the overall limit did not exist. And so we were already kind of talking about this idea, but now we're going to formally hit it, So, when we say something like limit from the right, okay, that means that x approaches c from values that are greater than c. Okay, which makes sense, right? If you're coming from the right, if you're approaching from the right, okay, of c, values right of c will be greater than c, right? That's just the way things are, right? So the way we indicate this right-hand limit, in fact, we can evaluate limits just from the right. Okay, just from the right-hand side. The way we do that, if we want to evaluate the limit as x approaches c just from the right, we put a little plus sign in the kind of exponent place of c. Okay, so that means the limit of x approaches c from the right. So we can, alpha f of x equals L. And of course that can, equal a number. Likewise, we can have a limit from the left. And that means that x approaches c from values that are less than c. Which again makes sense, right? Approaching from the left means values to the left of c will be less than c. And of course, you may be able to guess that the limit as x approaches c, the symbol for that will be a negative sign in the exponent. Okay. Now, we want to be careful here, because students oftentimes, especially the second one, get it confused with like the limit as x approaches negative c. Okay, so please be very careful, right? The limit as x approaches negative c, the negative sign would be in front of the c. The limit as x approaches c from the left, the negative is in the exponent, right? Okay, so please just be careful with that, because you might be on the quiz and like focused on trying to get everything, doing all your answers and like get everything right, and you might just accidentally see something like this and think that we're really just approaching negative c as opposed to c from the left. So please just be on your toes for that, okay? It's very easy to kind of get those things switched around and stuff, so just be careful. Okay? So, let's do some examples of this. Okay, so we'll just evaluate the limits. So the limit as x approaches 3 from the left. And we'll start with just a nice function. Okay. So x squared minus 3x plus 1, right? It's a parabola. Is a parabola ever discontinuous? Does it have any jumps or holes or gaps in or anything like that? No, right? And so, since this thing has no, possible discontinuities in it, we can evaluate this limit from the left just like we would a normal limit. So in other words, direct substitution still applies here. There's no special kind of, new thing we really need to do. We just, same idea, we just substitute it in. So it'll be, 3 squared minus 3 times 3 plus 1. And so we end up with just 1. Okay. So that's the good news, right? In a nice continuous function, evaluating the limit as x approaches 3 from the left or from the right, it's the same idea. So, we'll go ahead and we'll do this other one here too. So we'll approach 3 from the right, and we'll do the same function. Okay. The same argument still applies here. Whether we're approaching 3 from the left or 3 from the right, okay, coming in from the left, coming in from the right. Okay. The function is still continuous, and so a direct substitution would still work here. It would still be okay. And in fact, right, since this function is continuous everywhere, we had better have the same limit as we're approaching from the left and from the right. It better both be 1. Okay. Because it's continuous. Alright, so let's consider some other things. So I guess I'll even write that down here. So for a continuous function, just use direct substitution. Right, we can just plug it in. When a function is continuous, evaluating that function at the point is just like finding its limit at that point. They're the same value. Okay, but now let's try the same thing. Let's change our function up. Got those fun piecewise functions. Okay. So we can consider this piecewise function here. So you can just look at the piecewise function here, right? And let's kind of imagine it. All right, we have one piece, x squared minus 5, so it's going to look like part of a parabola. Okay, part of a parabola that was shifted down 5. Okay, and the parabola is the piece that we use, right? It's the parabola piece for x values that are less than 1. That means that those are x values to the which side of 1? To the left of 1, right? Because if we're going less than 1, it's left of 1. Okay? Then for that second piece, 2x plus 5, that'll be a line. But that 2x plus 5 will only be true for values that are 1 or to the right of 1. Right? For x values greater than or equal to 1, so to the right of 1. So left of 1, we're going to use this. Right or equal to 1, we're going to use this piece. Alright, so let's see here then. The limit as x approaches 1 from the left of f of x. Thank you, Abby. The limit as x approaches 1 from the left with f of x. What's that going to be? What do you guys think? Okay, it's a mystery. What about the limit as x approaches 1 from the right of f of x? Any ideas there? Yeah, Sean, what do you say? Okay. Okay, so then what would that look like here? What would I write then?
X squared minus 5.
Uh-huh.
Pretty sure you just subtract
Yep, exactly right. We're just going to plug that 1, bless you, into the top equation because we're approaching that 1 from the left, and since we're strictly approaching it from the left, we will only consider x values that are less than 1, and therefore we'll only use that x squared minus 5. Exactly right. So this will be -4. Okay. For number 4, since we're strictly approaching 1 from the right, and only from the right, well, those are always going to be values greater than 1, and so we'll use this bottom one. And direct substitute, like you said. And so we get 7. Okay. Now let's go back in time a little bit to like yesterday or 2 days ago. And let's evaluate the overall limit. Just as x approaches 1, not from the left, not from the right. Well, I guess kind of both simultaneously. What will we say here? So right, at 1, if we are exactly at 1, 2x plus 5 would be the function that we go to. But remember, we are approaching 1 here. That means we are approaching 1 both from the left and from the right here. From the left, as we approach 1, we're at -4. From the right, as we approach 1, we're at 7. So then the overall limit is going to be what? 5.5? Found the average that you're averaging or something like that? Yeah. Okay. Or yeah, well, maybe I think 3.5 if you average. But that's not. But that's good. Good thinking. Does not exist. That's right. The limit does not exist. Okay. Because if the left hand limit and the right hand limit disagree, right? Think back to that idea about the absolute value graph that we did yesterday, right? The left hand, right hand did not agree. And so they don't agree, all right, we can't kind of, come up with a limit there. And so the limit does not exist. Okay, so left hand and right hand must agree. I'll write that down here. Left hand and right hand limits must agree for a limit to exist. Okay? Left hand and right hand limits must agree for a limit to exist because a limit is a combination of both. And so when we have disagreement, that means the limit does not exist, right? We don't have a definitive number, a single number. Okay? That's just for you guys, for your edification. Okay. Potentially, it could be an explanation that you have to do. Yes. But when if it's just asking, just evaluate the limit, then you can just say it does not exist. Okay. All right. What about this limit? Remember, like 6 here. The limit is x approaches 5. How will we evaluate that? Notice it's not from the left or from the right. It's x approaches 5. How do we evaluate this? Yep, Sean? Why do you say it doesn't like this? True. They don't agree at what x value? At 1, right? It's just at 1. What about x when we're approaching 5? Yep. Yeah, we use the bottom piece, right? The bottom piece is strictly for x values that are greater than or equal to 1. Can we approach 5 from the left and from the right using that same 2x plus 5? And the answer is, yeah, we can, right? X greater than or equal to 1 means we can approach 5 both from the left, right? We can use values like 4, 4.9, 4.99, 4.999, right? Those are all greater than or equal to 1. Simultaneously, we can also use like 5.1, 5.01, 5.001, right? Those are also greater than or equal to 1. And so this 2x plus 5 is all we need to consider for this particular limit. And so it'll just be 2 times 5 plus 5. We're going to use that bottom piece. So it'll be 15. Oops, off the screen. There we go. Okay. Just be that bottom piece. All right. This one's for you guys to try here, and then we'll move on to the graphs on the back. Okay, go ahead and evaluate that limit for number 7, please. Take a minute or 30 seconds. Volunteers for number 7? What do we say here? Brave souls. Not so brave. 20 is right. Okay, that's right. Okay, the x value is approaching -5. -5 is less than 1, so we're going to consider this piece. And any x values left of -5 and any x values immediately to the left of -5 and immediately to the right of -5 will still be within this parameter of x less than 1. So we can just evaluate it here using direct substitution. So it's 25 minus 5, which is just 20. Okay. So again, 3, 4, and 5, right? They were kind of unique. They were special, right? Evaluating these limits were special because we were evaluating that limit at the point, at the x value where we switched from this to this, right? We switched from x squared minus 5 to 2x plus 5 around that 1. And so that's why we had to be extra cautious, bless you, extra cautious about how we evaluated things, right? Approaching 1 from the left, those are x values less than 1, so we had to use the top function. Approaching 1 from the right, those are x values greater than or equal to 1, so we had to use the bottom function. Then the overall limit, in this case, did not exist because the left hand and the right hand disagreed. Will that always be the case? No. sometimes the left hand and the right hand limit will agree. Okay? The fact that the left hand and the right hand disagree here indicates that the piecewise function does not join up. There's a jump between the two pieces. Okay? Should the two piecewise functions join up, should they connect, then the limit should exist. Okay? And then for 6 and 7, right, these are just evaluating those limits like you normally would, right? 5 is greater than or equal to 1, and so are the values immediately to the left of 5, immediately to the right of 5. So we use the 2x plus 5. Negative 5 is less than 1, and so are the values immediately to the left of negative 5 and immediately to the right of negative 5. Excuse me. So you would use the top function to just a direct substitution. Okay? So really, if you look and consider, right, there's no new strategy here when it comes to evaluating limits from the left and from the right. It's a matter of still using that direct substitution, but it's a matter of, you know, sometimes which part in this piecewise function, for example, that you plug into. But sometimes, right, evaluating a left-hand and right-hand limit is just like a direct substitution. You get the exact same number because this is a nice continuous function, right? There's no jumps, holes, or gaps or anything like that, and so it should be the same. Okay. Any questions on that before we move on to the back? Okay, you're all thoroughly confused. Excellent. Let's move on then. Okay. So, I had a special spare one that I gave myself. All right, I'll just go get it. Could you hand me one, Abby? I thought I had one, but then I don't know where I put it. Thank you. Okay. So, actually, you know what? Oh, Mr. Whitmire. You're crazy. All right, here we go. So, let's look at our first graph there up top. Okay, we'll call this graph f of x. All right, so let's say this thing is f of x. Okay, another piecewise function, but this one defined just by its graph, not by any sort of, you know, I guess function definition or anything like that, right? But it's very much a piecewise function just because it's so crazy, right? Okay, and of course we'll assume we're counting by ones here as well. I think that's what we're supposed to be. There's like teeny little numbers in there, but I think they're supposed to be counted by ones, just so you know. Okay. So we'll do 3 here together, and then I'll have you guys try some. Bless you. So let's say the limit as x approaches this of f of x. Okay. So Ralph, this number 1 here, this is the limit as x approaches what? What's it saying here? Aha. And approaching what number?
1.
Positive 1 from the left. Very good. Okay, so that's the first thing. We just got to make sure we get that right because we got to know what we're like looking at there. Okay, very good. And so let's go to so Jackson then. What is the value of the function? What is the y value that we're approaching as we approach 1 from the left? Negative 2. Exactly right. Here is the x value of 1. If you look at our function here, from the left, it's this horizontal component, right, horizontal piece, and it's negative 2. So that's the answer. Y value there is negative 2. From the left. From the left. All right. Well, of course, we got to ask the other question here. 1 from the right. And so let's go to Grace. What's the value of our function here as we approach 1 from the right? Negative 1. That's right. Very good. Okay. From the right of 1, we're approaching from this kind of quadratic piece, and it's going down to that negative 1. Even though there's an open circle there, we don't care about that because we're just approaching that x value of 1. So the fact that open circle is approaching negative 1 y value, that's exactly right. Okay, very good. All right, let's try one more here. What then is the overall limit as x approaches 1? So not just from the left, not just from the right, but the overall, the total limit there. What would we say? Let's go to Anna. What do you say? You would say 2? So as we approach 1, from the right, it was -1. As we approach 1 from the left, it was -2. So what would we say the overall limit would be then? So the left hand and the right hand are different values. So that means the limit overall, we should say what? Doesn't exist. Very good. Does not exist. Okay. Very good. All right, you guys try. All right, so let's see here. Oh, I guess we should call this 4, not a 1. So try find the limit as x approaches that. Actually, I have 4 things. Oops. Okay, so try 4, 5, 6, and 7 there. Overall limit is essentially a combination of these 2 things. If one of these 2 things, if these 2 things are different, then the overall limit can't exist because they don't agree. If the left and right both agree, then you know what the overall limit is. It's that number, yeah. So you'll notice well here, you're going to have to write a limit times the value of the function at precisely -1. Exactly right. So, in a situation like this, right, we also have the idea of continuity, where sometimes the function and the limit are the exact same value. Sometimes they're not. And they won't be the same simply if it's just continuous. Okay, so the value of function 2 will go along exactly like this. Any other questions? Okay. Let's take a look here then. All right, let's go to Danny. Danny number 4. What do you say? Limit is x approaching -1 from the left. -2. Very good. Let's go to Megan. Megan, what about number 5?
Positive 2.
As we approach -1 from the right. So if we look here, here's -1, right? And we're approaching it from the right. We're going to have to, in order to approach from the right, we have to use this piece of our graph. So it's -2, exactly right. Okay. Okay. Devin, about number 6? -2, right. If the left hand and right hand agree, folks, the overall limit is easy. It is the same thing, right? If the left hand and right hand disagree, the overall limit is easy as well. It doesn't exist. Okay, so. And then how about Luke for number 7 there? What's the value of the function at exactly -1? Number 2, right, positive 2. Okay? Very good. All right. Questions on any of that? So here we see a lot of things going on, right? So first of all, going to what we talked about today, the left hand and right hand limit don't always have to agree, right? In this case, as we approach 1 from the left, it was -2. As we approach 1 from the right, it was -1. Since they disagree, we say the overall limit does not exist. Sometimes, though, the left hand and right hand limit do agree, and therefore the overall limit will be the same value, -2. Right? But still we see this behavior where the limit and the function value don't always agree too, right? We have this open circle, we have this filled in dot here, right? There's a discontinuity here. So that would indicate that the limit and the function, one of those may not exist, and or one of those may not be the same value as the other. Okay? So in this case, both the limit and the function value exist at -1, right? The limit is -2, the function value is +2, but they are not the same value. Okay, one, the limit goes to -2, one, the function goes to 2. 3 more things here we're going to look at, 3 more little problems. Okay, so we're going to call this bottom function here g of x. And you're going to want to consider both these functions kind of simultaneously. I'm not going to like do anything unique with just g. We'll actually use g and f together here. So just as an example of some, combinations of things. Let's say we want to find the limit as x approaches 0 of f of x plus g of x. Okay. To do this, we don't have to do anything special. We don't have to try to imagine adding f and g together. We don't have to worry about that. We can just evaluate the limit of f at 0, evaluate the limit of g at 0. So what is the limit of f as x approaches 0? -2, yeah, right, exactly. So 0, right, here's the x value of 0 on a function f, right, and that all, to the left and to the right, it's both -2. All right, and then to that we're going to add the limit as x approaches 0 of g. Well, according to our function up here, what's the limit as x approaches 0 of g? 3, right? Yeah, there's 3 up here. So, from the left and from the right, approaching 3. And so we can say it's 1. Take an individual limit and just add them together. Okay? What about the limit as x approaches 1 from the right of f of x plus g of x all over 3? Well, again, we can take the individual limits here. So what's the limit of f as x approaches 1 from the right? -1. Sorry, I thought I heard it. I just want to make sure. And then g of x as we approach 1 from the right. 1, right? As we approach 1 from the right, the x value of 1 from the right, we're approaching a value of 1. And -1 plus 1 is 0, so divided by that by 3 is still just 0. Okay. Excuse me. Last one here we'll look at. The limit as x approaches -1 of g of f of x. So since f is on the inside, we should evaluate the limit as x approaches negative 1 of f. So what is the limit as x approaches negative 1 of f? Negative 2. And so we just define g then of negative 2. Then what's g of negative 2? About. So g of negative 2 is about negative 1, I would say, roughly, right? Here's negative 2, so g of negative 2 is about negative 1. Let's say about. All right. Questions on any of that? All right. So if not, well, even if there are, that's okay. We'll get you here some review. So the paper I'm about to pass out, all right, will have a good mixture, all right, of different kinds of limits that you will be expected to know. Okay. Let me just kind of show you here. All right, you can see that it starts out with, you know, some limits, okay, and it's all mixed and matched, right? You don't necessarily have, you know, them telling you exactly what to do here. Okay, if you flip it, well, when you flip it over, you can see that there's some limits from a graph that you get to evaluate too. Okay, evaluate different, well, not just limits, but also function values here. One thing I will make mention of here that is missing, okay, that you should still be able to do for tomorrow's quiz is the rationalization, right? There's no rationalization problems on here. Okay, there's no, like, you know, having to multiply by the conjugate, stuff like that. So that's another thing you definitely want to take a look at as well. Okay. Did you make a note to yourself about that? Okay. This will be your homework. And redacted for confidentiality. If you need to, folks, make a note to yourself, right, that you also should look at rationalization tonight, too. Because there aren't any